Hi everyone, in this video we are going to discuss another type of force known as the viscous force, and the easiest way to actually start understanding viscous force is to really just think about air resistance. So for the learning objective, we are still at objective C. So this time around, focusing on viscous force including air resistance. So what exactly is viscous force? It is just another kind of resistive force that opposes relative motion. So you can see that it is kind of similar to friction. So indeed, there are some similarity between viscous force and friction, but there are also some differences. So first and foremost, viscous force will only be present when an object moves through a fluid. So fluid can be liquid or gas. So the example is like air resistant. So this presents itself a first difference between viscous force and friction. Friction is normally considered between two hard surfaces, whereas for viscous force, it is when an object moves through a fluid. So if let's say I have a solid sphere here, moving towards the bottom left in a fluid, then in that case, there's going to be a viscous force acting against its motion in this case. The similarity between viscous force and friction is also the fact that viscous force is dissipative in nature. So meaning to say that when viscous force is present, it is inevitably going to produce thermal energy. And one differences between viscous force and friction is that for viscous force, it will actually increases with speed. Okay, for friction, it should roughly stay generally constant when the object is moving. So regardless of the speed, the friction should be roughly constant. So one thing that you need to take note here is the way I describe how viscous force changes with speed. What I'm saying here is viscous force will increase with speed, but I did not say that viscous force is proportional to speed. So this is one common mistake that students always misinterpret, okay, the lecture notes. What the lecture note says here is viscous force will increase with speed, but it may not be proportional to speed. Another difference between viscous force and friction is that viscous force will be zero when the object is stationary. So unlike friction, so in the previous video, I did mention an example of Xiaoming pushing his cupboard. So at the start, if Xiaoming's force is small, the cupboard would not move. Okay, and that is really because there is static friction working against Xiaoming's force. So in that case, the object was stationary, but there is still a certain amount of static friction acting on the object itself. So in work example 3, you are required to explain the origin of air resistance. So the way to think about air resistance is really that it is the force exerted on a moving body due to the collision of the body and the air molecules in its path. Okay, so do take note of the keyword here. It is very important that you mention the word moving bodies, okay, because air resistance is a type of viscous force, and as you have already learned in the previous slide, there will be no air resistance, there will be no viscous force if the object is not moving. So therefore, moving body, the word moving is actually an important keyword. So let's discuss some factors affecting viscous force. So first and foremost, okay, something I have already mentioned, the speed of the object. So viscous force will increase with the speed of the moving object. Okay, it will increase, but you should never say that it is proportional to V, because certain scenario the viscous force can be proportional to V squared. So there is a variety of way to calculate viscous force. And in A level, generally you're not required to calculate viscous force, but if you actually are required to, the question will actually refer to you the formula. Okay, so there is no need for you to assume anything if you actually need to calculate the equation who have been given to you. Otherwise, if you need to describe viscous force, how you should describe is that viscous force will increase with speed. Okay, do not ever say that viscous force is actually proportional to velocity. The second factor that will actually affect viscous force is the viscosity of the fluid. So in your lecture note, it was written there that the viscosity of a fluid is a measure of how easily it flows. Not that it is wrong, but I prefer to rephrase it in another way. Okay, the way that I'll suggest you to copy down and rephrase is that the viscosity of a fluid is a measure of a fluid's resistance to flow. Okay, the reason why I want to change it this way is because I personally feel that if you read it this way, then it will give you the natural inclination to think that the higher viscosity refers to a higher resistance to flow. So for an object moving at a given speed, it will actually encounter a greater viscous force when traveling through a fluid of higher viscosity. So for example, if let's say an object moving at the same speed in water, okay, it will definitely experience a greater resistance than the object moving through air. Also, please take note that viscosity is not the same thing as the density of the liquid. This is a common misunderstanding. Okay, viscosity is really just about the measure of the fluid's resistance to flow. So, for example, oil is definitely less than water. Okay, but normally oil is more viscous than just pure water. So that is an example whereby oil having a higher viscosity but lower density. Okay, viscosity is independent to density. And lastly, the last factor is actually the shape and size of the object. And I guess this factor is pretty obvious because otherwise why would engineer design all aeroplane and bullet train with a pointed nose tip and not in a shape of a parachute which actually traps air as it moves? Yeah, so actually an object that is actually more aerodynamically or streamlined design will really encounter less viscous force. So now let us look at how the forces actually changes or how the forces acts on an object changes as the object falls through a fluid. So consider a sphere of weight W falling through air or any fluid for that purpose. So initially the force, the weight will actually be greater than the air resistance. And in fact, if let's say I drop the sphere from rest, initially the air resistance will actually be zero because if you recall, we've mentioned that viscous force is zero when the object is stationary. So if I were to drop something from rest, instantaneously initially is at rest, air resistance will be zero, the net force acting on the object would just be the weight. So the sphere would naturally accelerate downwards because there is a net force downwards, weight minus air resistance. So in this case, you can see that I've drawn the air resistance of a smaller magnitude as compared to the weight. And because as it accelerates, the velocity will increase. And as velocity increases, the viscous force acting on the object, in this case the air resistance, will increase up to a certain scenario whereby the air resistance is just equals to the weight. When the air resistance is equal to the weight, the object is considered to be in equilibrium, the net force is zero, acceleration becomes zero, the velocity reaches a maximum. So as you can see, velocity increases, air resistance increases. The air resistance will increase in magnitude until to the stage that it is actually equals to the weight. So when the air resistance is equal to the weight, net force is zero, net acceleration is zero, the velocity no longer increases. And because velocity stay constant, air resistance will stay constant. So the scenario here will be, it will finally reach the point whereby net force zero and will stay zero. So the velocity in this case where this occurs is actually called the terminal velocity. So in the graphical way, this is how the VT graph will look like. And if you can see, the gradient initially is the sharpest, and as time moves on, as velocity increase, the gradient of the VT graph tends towards zero. And at a point whereby time, at the point in time whereby gradient is equal to zero, terminal velocity is reached. So something for you to take note, if this is an object that falls from rest, okay, on Earth, you should see that this gradient, this particular gradient should read 9.81, okay, because that should be the gravitational acceleration. So this will help us to explain the work example 4, show how forces acting on the sphere varies at different stages of a fall with air resistance. So at the start of the fall, velocity is zero, so only the weight of the sphere is acting on the object. So the acceleration will be g 9.81. So before the object reaches terminal velocity, it will actually accelerate. Okay, v is greater than zero, resulting in some air resistance acting on the object, but still smaller than the weight. So the net force will now be smaller than the weight, but still greater than zero. Acceleration less than g, but still greater than zero. So the velocity will continue to increase until to the stage whereby it is at terminal velocity. So at this point in time, the air resistance is equals to the weight. The net force will be zero, acceleration will be zero. So the velocity of the sphere increases over time. Viscous force acting on it increases to a maximum constant value when F is equals to W. And thus the object is in equilibrium. The velocity at which this occurs is called the terminal velocity. So for a fluid with low density such as air, the upthrust on the sphere is negligible. For now, you may not know what upthrust is meant. Okay, so that is fine for now. Okay, upthrust is something that you will learn in much greater detail at the later videos. So we'll leave it for now. Just that understand that for air with for fluid with low density, we will just consider upthrust to be negligible. But for fluids with larger density, such as oil, we have to consider something that is known as upthrust. So here we have some interesting examples like a skydiver. It will attain terminal velocity between 150 km per hour to 200 km per hour, as well as how raindrops, okay, because of air, it will reach terminal velocity well before it reaches the ground. So it actually saves us, okay. The atmosphere around us is providing a protective layer so that the raindrop wouldn't drop at a very high velocity, gaining very high momentum, so that it wouldn't hit us and crush us. So we move on to example 5. In example 5, an object of mass 0.5 kg is falling under gravity with velocity v through a viscous fluid such that the viscous force it experiences is given by F equals to kV, where k is equals to 26 Newton second per meter. Calculate the terminal velocity of the object. Calculate the acceleration of the object when it is falling with velocity 0.14 meter per second. So something of note, like I mentioned just now, if you ever require to calculate viscous force, an equation will be given to you, such as this example. So for part A, I need to calculate the terminal velocity of the object. So at terminal velocity, assuming upthrust is 0, weight is equals to the air resistance. So my weight equals to mg, so 0.5 times 9.81 will be equals to kV given in the question. K is 26, so it is essentially equal to 26V. So in this case, you can see that we can just algebraic manipulate it and get V. So V will be equals to 0.19 meter per second. So for part B, we need to calculate the acceleration. So by Newton's second law, we do know that the net force is equal to ma. So since the velocity is 0.14 less than the terminal velocity, I expect the weight to be greater than the air resistance. So I'll take downward as positive. Therefore, W minus F, air resistance, equals to ma. So now substituting in the value, weight is equal to mg minus kV, air resistance, will be equal to 0.5a. So once again, algebraic manipulate, you will get a equals to 2.5 meter per second squared. So for this particular example, it is actually missing. The full working is actually missing from a lecture note. So please pause the video and take some time to copy the solution into your lecture notes. So with that, we are done with the discussion of viscous force. In the next video, we are going to talk about tension and compression, as well as a new law known as the Hooke's law. Similar to the previous video, at the end of this lecture, I'll be showing you two videos. One of the videos will be talking about how the atmosphere is actually protecting us from some outer space attacks such as the meteorites. And there's a second video that talks about the forces and the physics behind air resistance and parachutes. Okay, so if you are interested, continue to watch the video. Otherwise, it is fine that you log off from here and then move on to the next video, tension and compression. Okay, thanks, bye!
There's a bunch of rocks floating up there in space. What separates, pretty lights from, we're all gonna die! Hey everyone, Julian here for D News. Shooting stars have a magical ethos. We're told to make a wish when we see them streak across the sky, but you should probably already thank your lucky stars, because if we didn't have an atmosphere, they'd be a lot more dangerous. First of all, shooting stars is a misnomer because they're not stars zipping about. They're meteoroids, bits of dust, usually left by comets or asteroids. We see them at 70 to 120 kilometers away when they're just starting to dip into our mesosphere and the air starts becoming dense enough to give the meteoroids some resistance. And it only gets more dense the closer to Earth they get. These meteoroids are traveling fast, between 11 and 71 kilometers per second, and the friction from rubbing against all that air at those speeds heats them up as much as 1600 degrees Celsius, causing them to burn up and leave a streak of light called a meteor. Meteoroids the size of sand grains and smaller enter our atmosphere every day by the truckload. NASA estimates 100 tons of dust hits us every single day. But they're so small they don't have enough momentum to keep up their speed when they hit the air. Instead, they slow down and make it all the way to Earth. If you want to see a show, there are about a dozen major meteor showers a year, and they happen predictably because the Earth keeps passing through the wake of the same comets. Some particles the comets left behind are about the size of pebbles, so they're big enough to keep up their speed and ignite. It's pretty impressive that we can see them from as far as 120 kilometers away. That should tell you a little bit about how much energy they have at those speeds, even though they're itty-bitty. So imagine how much energy meteoroids have when they're the size of a car. They can cause huge fireballs brighter than the planet Venus. Meteoroid sizes vary a lot, and they can be up to 100 meters across before they're classified as asteroids. But so long as they're less than 25 meters across, the atmosphere usually burns them up. Sometimes, upon entry, they break apart with a bright terminal flash called a bolide. Bolides are harmless, but the optical energy they give off as light can be in the range of 100,000 gigajoules, 100 times more energetic than the bomb dropped on Nagasaki. Bolides are detected about 28 times a year. So obviously, our atmosphere is doing us a solid. More than just giving us the air we breathe and protecting us from UV rays, the atmosphere is running interference on meteoroids and asteroids too, making sure our planet isn't as cratered as my face was in high school. But who watches the watchmen? Turns out the atmosphere needs a little help too from the Earth's magnetic field. The magnetic field produced by the spinning iron core diverts the charged particles the sun constantly shoots off into space away from our atmosphere. If we didn't have it, our asteroid shield would be blown away by the solar wind. So the Earth is shielding the atmosphere, which is shielding the Earth. It's pretty sweet. Mars doesn't have much of an atmosphere because it has no magnetic field, and when you look at that, it gets hit with meteorites 200 times a year. Even with the atmosphere intercepting most space rocks before they can impact the surface, Earth still gets hit with a biggie every now and then. NASA estimates an asteroid the size of a football field gets through and causes significant damage to the local area once every 2,000 years. If it's over a kilometer wide, it could have global impacts. The asteroid that wiped out the dinosaurs was estimated to be 10 kilometers across. NASA isn't leaving our fate to chance, and it's working on tracking dangerous near-Earth objects. They hope to one day send astronauts to study a dangerous asteroid before sending said asteroid into a harmless orbit around the moon. Yeah, it sounds like NASA got the idea from a Bruce Willis and Ben Affleck movie. So now you know why meteoroids burn up, but what if they make it all the way to Earth? Trace has the scoop on meteorites here.
If a meteoroid is large enough to make it through our atmosphere and dent the solid surface of our planet, at least the size of a marble usually, then things get real.
So are you afraid of meteoroids or no big deal? Let us know in the comments, subscribe for more, and I will see you next time on D News.
You might be wondering why I'm sat in the door of a plane strapped to someone who can only be described as a madman. Frankly, at this moment, I was asking myself the same thing. I'm Ross, and this week we're exploring the science of skydiving. So how is it possible to jump out of a plane and survive? Gravity is a pretty powerful force, and 15,000 feet is a long way to go before hitting the ground. We've all experienced gravity. What goes up must come down, and it's a product of the object's mass. This apple and the Earth are both being attracted towards one another because of the force of gravity. But since the apple is far less massive than the Earth, the apple appears to fall towards the Earth. The acceleration due to gravity is 9.8 meters per second. In other words, with each second that passes, I'm going to be traveling 9.8 meters per second faster. But this doesn't mean that I'm going to keep speeding up until I hit the floor with a splat. So here I have a giant fan and a smoke machine. Now, if I take this inflatable shuttle and place it in the stream of air, we can see that it flows over it very easily. So there's not much air resistance there. But if we switch this for something with a bit more surface area, we can now see the air is a lot more turbulent and is facing greater air resistance. This air resistance is what's going to help me survive the jump. As I fall through the air, it's going to be pushing back on my body in the opposite direction. And the faster I fall, the greater the force of air resistance pushing back. After 3 seconds, our speed is already at 60 miles per hour, but air resistance is already affecting our acceleration. By 8 seconds, we're at 102, and it takes a further 7 seconds for us to reach 120 miles per hour. At this point, the force of gravity is equal to the force of air resistance. This means that we've stopped accelerating. and so our speed is constant. This is called our terminal velocity. This belly down position also helps increase air resistance, but even so, hitting the ground at 120 miles per hour is still a very bad idea. The instructor has already released a small parachute which helps create a little extra drag. When we get to roughly 3,500 feet, the instructor deploys the main parachute. All of a sudden, the huge surface area massively increases the air resistance and we quickly decelerate. In just a couple of seconds, we go from 120 miles per hour to just 5. And I've got to tell you, that's the biggest wedgie you can ever experience. After several minutes of gliding around, we land safely back on Earth. For more science stunts, why not watch me walking across red-hot coals? Stay tuned over the next few weeks as we'll be investigating all things foodie, from beehives to milking cows. So for more science every week, click subscribe. Thanks for watching.